In this lecture, we are going to look at binary recursion. The last lecture, we looked at linear recursion. In linear recursion, the example we saw was factorial, where one recursive call is made by the function. So here we look at a function where binary, that is two recursive calls are made. So the example we are, the problem we are going to look at is trying to find out the nth Fibonacci number. So what is a Fibonacci number? So Fibonacci sequence are the following. So it's 1. So first two Fibonacci numbers are 1 and 1. The next one is this 1 plus 1, 2. The fourth one is 2 plus 1, 3. Fifth one is 3 plus 2, 5, 8, 13, etc. etc. Okay. So the first Fibonacci number is 1. The second Fibonacci number is 1. First two. And from third onwards, we know what has to be done, right? So f of 3 is 2, which is f of 1 plus f of 2. And what about f of 4? F of 4 is equal to 3. This is equal to f of 1 plus, f of 2 plus f of 3. And fifth is 5. Okay, f of 5 is f of 3 plus f of 4. As you could see, f of 5 is 5. Okay, so that's sometimes you are confused whether a Fibonacci sequence of 0 is 1 or does it start in 0 or does it start in 1? I mean, I get confused, so I remember it as f of 5 is equal to 5. Now, so what is a general Fibonacci sequence thing? The sequence is f of n is equal to f of n is equal to f of n minus 2 plus f of n minus 1. This is that's how you can get the nth Fibonacci sequence. Right. Now, we want to write this as a C function. So I'm going to name this function Fibonacci, and what is the input? What is the input to this Fibonacci function? So the input is going to be an integer because I am interested in the nth Fibonacci number. And what's the output? Output is an integer which is the nth Fibonacci number. Right. Okay, so here you should write what this function does. The function basically takes an integer n and returns the nth Fibonacci number. Okay. Now, as we said, every recursive function has two blocks of code which we need to fill up. So the first thing is the base case. First, that's what we need to think first. What is a base case here? What is the case which does not depend on the previous values? So as we see, f of n is equal to f of n minus 2 plus f of n minus 1 here, but not. So this is for all n right. This is for all n greater than 2. F of 1 and f of 2 does not depend on the previous values. Okay, so so now we know what is the base case now. The base case is the case which does not depend on the previous case, that is 1 and 2. So I will write here. So I will write here if that is if n is the first Fibonacci number, what should be written? If n is the first or second Fibonacci number, you return 1 because the first and second Fibonacci number is 1. Now we are interested in, so if this is neither of these two cases, that's when it comes here. It comes down if it's neither n is 1 nor 2. How do you write this? So I'm going to take the n minus 1th value. So I know f of n is equal to f of n minus 2 plus f of n minus 1. So what is the natural way to write this thing? I'm going to have one integer variable which is going to take this value, another integer variable which is going to take this value. I'm going to sum them up and I am going to return that. Right? So how am I going to get this and this value? I'm going to recursively call. Right? So so what do I call? Right? So I have a variable, basically the n minus 1th Fibonacci number, right? So let me call this n1. Okay, so the variable n1 is going to store the n minus 1th Fibonacci number. And how do I get that? I'm going to call this. How do I get that? I'm going to call this function Fibonacci. I'm going to call the function Fibonacci with the value n minus 1. Right? Next thing is I want the n minus 2th Fibonacci number. So that is n2 is equal to okay. So now I have got the n minus 2th value and n minus 1 value. What should I return now? Right? What should I return? I should return the sum of these two values because that's exactly Fibonacci number. Okay. Now let's work out how the block looks like. Okay. So before that, maybe we can check whether our function is so we look at the three properties. We need to check to see if our Fibonacci sequence, our function is written correctly. What are the three properties? It's basically a recap. What are the three properties we need to look? We need to see check whether the base case is correct. Right? So this is the base case. You need to check whether the base case is correct. As you could see, there are two base cases. We check that and we can see it's correct. So that's fine. Next property we need to check is, has the input parameter value decreased? Here the input is the integer n. In the subsequent call, in the recursive call, has the input parameter value decreased? It has decreased in both the calls. There are now two recursive steps. Okay, so this is the recursive step, and here there are two recursive calls to the Fibonacci function, and we could see that in both the cases the input parameter value decreases. So that satisfies our second condition also. And what about the third condition we need to satisfy? And the third condition we need to satisfy is that the global correctness or the total correctness of this function. And how did we do that? So for that we need to assume that the recursive step the return values in the recursive step is correct. Okay, and assuming that, can I argue that this function returns correctly? So I am going to assume that n1 value is the n-1 Fibonacci number and n2 value is the n-2 Fibonacci number. Okay, so I have the value for n-1 and n-1 and n-2, and using that I have returned n1 plus n2. Is my function returning the correct value then? It is. If I assume these two things are returned correctly, then this return is also correct, because that's exactly what this recursive definition gives me, right? So f of n is equal to f of n-2 plus f of n-1 and 1, and our Fibonacci sequence, so our function is correct. We know that now. So next thing we can do is we are going to draw the block diagram which we saw for the previous example. We are going to see how it looks like in this Fibonacci case. I want to get the third Fibonacci number. What is the third Fibonacci number? 1 plus 1 plus. So maybe let's get the fourth one. Okay, it's going to be big, but let's take the fourth one, right? And so the fourth one will be the following. So I call this function with an n becomes equal to 4, right? N is equal to 4. I come here. No, this condition is not satisfied. This condition is not satisfied. I come here. I want to assign n1, the value of n1, and for n1 to get a value, this function has to be executed. What do I mean by this function has to be executed? If you have to see what the return value of this function is, I need to write one more block. The return value of this function is going to be assigned to n1. So to see the return value of this function, I am going to draw a block, a sub block now. Right, it's called with n-1. So I have n is equal to 3. So how does this block start? This block starts here. N is equal to 3. This function is this condition not true. This condition not true. This condition again. n-1. Again. So again this Fibonacci n-1 is called. So what is the n value here? 3. Again n-1 of that is called, that is 2 is called. So what is this value going to be assigned to? It's going to be assigned to this n1, right? So I can write basically here n1 is equal to this, and now again n1 is equal to n is equal to 2. In the subsequent block n becomes equal to 2. Now I am going to fill that block. I come here, n is equal to 2, right? I come here. Does this statement get executed? No. What about this? This condition is correct, so it returns 1, right? So I can write, okay, I'll reduce the size of this box. Okay, it's returned 1. Now what is the next step it's going to execute? So in this block of n is equal to 3, it's right there. n1 has been assigned the value 3. So n1 is equal to 3, right? n1 has just now been assigned the value 3. What is the next line to be executed? The next line, n2. Okay, if I put some line number here, 1, 2, 3, 4. This is line number 3, right? So we are in line number 3. I got n1 is equal to 3. So I have to move to line number 4, and that is n2. And for n2, again, for n2 to get executed, you need the return for this block, Fibonacci n minus 2. What is the value of n minus 2 now? We know n is equal to 3. What is n minus 2? 3 minus 2, 1. Okay, so it's n is equal to 1, and I am going to call this Fibonacci 1. Come here, if n is equal to 1, it's true. So this return 1 gets executed. So when return 1 gets executed, n2 is equal to 1. Okay. Now, so line number 4 is also finished. We come to line number 5 of that block, and line number 5 is return n1 plus n2. What is n1 and n2? n1 is 3, n2 is 1. So it returns 4, right? Okay, so we have now finished So what have we finished? We have reached n1 is equal to 4 here in line number 3 of this block, right? N1 is equal to 4 of this bigger block. I have reached again the bigger block, our starting block. Okay, after recursively going deep 2 levels of depth. Now here, okay, so that is again line number 3, right? What is the next step to be executed? N2 is equal to. What should N2 be? N2 is equal to Fibonacci of n minus 2. Okay. What is n minus 2? What is n in this block? 4. N minus 2 in this block is 2. So I am calling Fibonacci of n minus 2, 2. Okay. So if I am calling n equal to 2, I come here. This condition, no, it's false. This condition, it's true. Return 1. Okay. It has returned 1. Reduce the size. We have now got n2 is equal to 1. So this is line number 4 here. Okay. So now we have both n1 and n2 value. Okay, and now what is the value of n1 plus n2? The value of n1 plus n2 is, what is the value of n1 here? 4, and n2 is 1. So what is the value of that? Okay, this is what I got. Okay, there's one mistake I made, so that's why the answer is wrong. I made the mistake here. When I came here, n is equal to 3, n1 is returned value 1, right? So n1 should be 1. I put 3 here. Somehow, I don't know, I made that mistake. So this should have been 1 here. And then the return value of this is n1 plus n2, which is 1 plus 1, which is equal to 2, and here it is again n1 is equal to 2, and this here is 2 plus 1, that's equal to 3. Okay, so for n is equal to 4, the return is equal to 3. Is that clear? So that's how. So now so this is how our box looks like. What is the innermost box going to be? What are these innermost box? Those are the base cases. Right? There are base cases. And you could also see that inside one box there can be multiple small boxes. So that is because of, I mean, there are two, I mean, there can be at most two small boxes. That's why, because it's binary recursion, you have two recursive calls. That's why you have two. Okay, now I hope so. So this is binary recursion. You can think of more multiple recursion where there are multiple calls, and how will it look like? There are going to be multiple boxes here. Okay, so that's next level of recursion. Okay, so this much is good. So now maybe let's complicate it a little bit. I'm going to look at a different problem, a little more complicated, and let's try to write a recursive algorithm for that. Okay. What I will do is that I will explain the main idea here, and then we will code that up in a lab session. Assume that I have an array of integers. An array of integers. Okay, it can be 1 to 5, 1 to 10. What I am interested in is the following. Okay, you can view it as a set of integers 1 to 5. I mean, the array provides you an order. 1 is the first element, etc. But you can forget it in your mind. So you can think of it also as a set now. So it's a set of 1, 2, 3, 4 up to 5. What I am interested in is the following. You should output all the subsets of this set. So print all the subsets of its set. Okay. That's all you know. There's no return. I'm not interested in any return. But I am interested in printing all the subsets of the set. What are all the subsets of the set? So let me first take a small set and then see all its subsets. If array has two elements 1 and 2, its subsets are an empty set, two singleton sets, 1 and 2, and a set which contains both the elements 1, 2. What if I had 3 elements? If I had 3 elements, again there will be an empty set and 3 singleton sets and sets of pairs of numbers. So I have written 1, 2 here. So these are all the pairs of numbers, right? And finally the full set. Okay, so this is how you can, these are all the subsets of this set. It's clear that if I have like 1, 2, 3, 4, how to write all the subsets. Now I want to print all the subsets. So I give you a set like in the form of an array, and I am interested in print all the subsets. How will we solve it recursively? So the main idea we are going to use is the following. I mean, there are a few ideas, I mean, couple of things we need to do, but the main idea, I mean, the main crucial idea is the following, is that these sets can be split into 2 parts. Okay, this set can be equally split into 2 parts, 2 parts of equal numbers. The subsets can be split into 2 parts. The first part contains all sets which has, let's say, number 1, all sets which has number 1, and all sets which do not have number 1. Let's look at how many. So what are all sets with 1? With 1. So these are all sets with 1. How many are there? So the number is equal to 4. So for the number I will just use hash. Okay, the number is equal to 4. That's a notation. It's not about C or something. Okay, sometimes count is represented using hash. So this number is for the number of subsets is 4. Next part is all sets without 1. Again, the number of subsets is 4. Do you see a pattern here? What is the difference between the set on top and bottom? They only differ by 1. Set of all subsets is partitioned into 2 parts. The first part which contains all sets with 1 and the second part which contains all sets without 1. And as you could see, 5 union 1 is what is just above it. Union this set 2 union 1 is this 1 2 set. 3 union 1 is this set 1 3. Similarly, you union 1 to this set, you get the set above. So it's so every set here you can get from removing 1 from the set above, and every set above can be got from the set below by adding 1. So there is an equal the number is the same. All sets with 1 and all sets without 1 are their cardinalities are the same. They have the same number. Here it's 4, and this is the same even if you have taken a set of bigger size. If you have taken a set of 1 to 5, it's the same. So any finite set, you take all subsets, you can partition it into 2 equal parts like this. Okay, so what is our idea? What is our recursive idea now? Do you see it? What kind of recursive idea can you, if you know this fact, how can you print all subsets here? So the recursive idea is the following. I'm going to remove 1 from here, right? So this is my set X. What I can do is I can remove element 1 from this set, right? And then I can, so okay, and recursively I want all subsets of this X, right? What are all subsets of X? Because 1 has been removed, we get exactly these sets. The subsets of all sets without 1 are basically the sets right below, right? These. Okay, so what is a recursive way to print this thing? I'm going to remove 1 and I'm going to print everyone here, right? And then I'm going to add 1 to each of them above. I'm going to add 1 to each of these sets and then print that set. Okay, so that's the recursive call. So the recursive call is you take the set X, remove 1 and call it recursively, right? Print all subsets of the set X minus 1. Also print all subsets of X minus 1 with 1 in it. So that those are 2 recursive calls. A recursive function versus an iterative function. So what's an iterative function? An iterative function is a function which is not recursive. So versus recursive function versus iterative function. What I have written here is the function, the factorial function, which the factorial function takes an integer n and return its factorial n factorial. So I have written this. We have seen this function. I have just simplified it and removed the variables, etc. here. Now this function is a recursive function, and I claim the following. This function I can write it without using recursion. Can I do that? How can I do that? What I'm going to do is that I'm going to run a for loop from 1 to n and just keep on multiplying from 1 to n and return that value. Okay, so this is my factorial function. It's basically saying, okay, you look from all numbers from 1 to n, keep an integer fact which is going to just keep on multiplying from 1 to n. That's it, and then I return fact. So this is also a factorial function. It's not a recursive function because I'm not calling factorial again, but this does the job for us, right? This is also computing the factorial. This is also computing the factorial. So this recursive function I have written in an iterative way. Now here is a main property I'm going to say. I won't prove why. This is something you will see later in your a programming language theory course, for example. And the idea is the following: every recursive function you can convert it into an iterative function. Okay, any recursive function you give, I can convert it into an iterative function. An iterative function which will also always have this a for loop. Okay, it can be a for loop or a while loop or a do while loop. One of these loops will be required if you have to convert a recursive function into an iterative function. A for, a while, or a do while. It's also the case that actually you don't require all three of them. For loop would do. If you have a for loop can also simulate a while or a do while also. So any one loop if you have, you can using loops you can rewrite a recursive function into an iterative function. But then so we already have for loops and while loops, etc. Then what is the reason why we studied recursion, right? So the main thing is that we studied recursion because that's an easy way for us to think. It's easy for humans to think. It's the human way to think. It's the human way to think is that if I know there is a problem which is a sub problem which is easy to solve, can I use that to solve the bigger problem? That's how we think, and that's the idea behind recursion. I have a solution to a sub problem of the same type. For the same factorial I can solve it for a sub part. Then I can use that to solve for the bigger problem. That's one idea in recursion. It happens everywhere. That's a very powerful idea. It's a very powerful notion for humans to think, and that's to design algorithms, etc. That's a very powerful notion, and that's why we studied recursion, and that's why it's very important concept in computer science. Now this question of why did I bringing this fact that every recursive function can be converted into an iterative function? Okay, so one simple reason is that for the computer to implement a recursive function, there is a little overhead. What do you mean by that? A computer in implementing factorial is going to take a little more time than a computer implementing it in iterative fashion. Okay, assuming you write the iterative fashion well, if you yourself is writing the iterative very badly, obviously that's not going to be good. But if you write your iterative algorithm very well, that's going to be a little more faster than the recursive function. So if you are going for some coding competitions, for example, or taking part in these things, this might be the way to write factorial. This may not be the way, but so that's one slight reason why I told it's a little overhead. So for coding competitions, use this. But this is a way to think. If you can think along these lines, then convert it into this way to write.